So again, I am Nathaniel Bonita and I am part of the UPDMME FA Hub. And I'll title this talk, From Microstructure to Macro Impact, Advanced FA Hub Capabilities in Action. Yeah. So before I continue, I'd like to first briefly introduce the team. So we have Engineer Stan Ejera as our project leader. We have our FA Hub specialist, FA specialist, Doc Mitch, Engineer Mark Cabading, and Engineer Edwin Canyazal. And we have our FA manager and admin support staff, Ma'am Narisa Cuenga and Miss Kimi Figueroa. And for the full-time manpower, we have Engineer Christopher Jason Villanoy, and Engineer Denise Domagas, and yours truly. And we have our skilled technicians, Sir Prisco Capilo and Sir J.R. Espiritu. Ayan. So far within its first year of operation since the formalization of the project establishment, the FA Hub has successfully completed 3 field research projects as discussed earlier by our industry partners, and 1 in-house testing activity with another 1 currently ongoing. So moving on, one of the major objectives of the FA Hub is its integration into the department's classes, particularly through METI 173 and METI 179. And also, we have engaged selected students through an apprenticeship program to designed to develop their practical skills and competencies in failure analysis. So in line with our commitment to bridging the gap between the industry and the academia through research and knowledge exchange, we organized this symposium, the Interface 2026, to showcase real-world application of analysis in solving real-world problems. So far, our core capabilities encompass both on-site and in-house laboratory testing, allowing us to evaluate materials and investigate failure comprehensively. So on the field side, we provide field metallography or replication testing, which is a non-destructive technique that enables the examination of microstructures directly on the critical components while they remain in service. So this capability is particularly important for condition monitoring and the early detection of degradation mechanisms such as creep, carbide degradation, and even crack initiation. So it helps industries make informed maintenance and operational decisions without requiring component removal. So complementing our field capabilities, our laboratory services include non-destructive testing, microstructure analysis, which provides detailed characterization of the failure features. We also perform mechanical testing, elemental testing through XRF, SEM, EDX. So alongside the MRCF, we are utilizing the department's testing capabilities for our research works as well. So in terms of our failure analysis workflow, investigations begin with, of course, the collection of relevant information from the client, including service history, operating conditions, maintenance records, and details surrounding the failure, alongside field observations and laboratory test results to identify the failure mechanism and establish the root cause of the failure. So now I'd like to give you a little background on how we established the testing protocols we have applied so far. So starting with the in-situ field metallographic replication, we have the materials, and the main difference with the in-situ one with the usual metallography that we know is that again, the field replication is done on site. So it requires portable materials that we have here, donated by our industry partners, so that we can establish our protocols. So the steps involved in the in-situ metallography is initially just the same as the actual metallography. So we have surface preparation to clean the surface and remove the scratches. We have the etching to reveal the microstructure. But it gets different past this point because we need to replicate the microstructure that is revealed after etching. So we do replication. Ayan. So the general idea here, let me show the final replica sample that we acquired. So the general idea here is that the replicating agents, the acetone and the cellulose acetate film, finally copies the surface topography of the etched part so that it can be analyzed under the microscope once the replica sample is extracted. So, as seen in the figures on the slide. So these figures show how the actual microstructure, and this one, taken from the metal sample itself and the replicated, acquired from the cellulose acetate film, differs. So we can see that although there's somehow less clarity in the microstructure here, still it was able to replicate the general microstructure in the actual etched sample. So by our testing and experimentation, we were able to produce quality replicas that accurately replicates the microstructure that we need for subsequent failure analysis. So, yeah. So after practicing and perfecting our methodologies, we were then able to apply it on our fieldwork activities, as you can see here. So we are literally fighting for our lives, though we are, of course, employing safe protocols and proper PPEs for this. But as you can see, we are literally on the tubes, on scaffoldings, just to get the microstructure of the actual part without breaking the actual part needed. So this is an example of a boiler tube and the replica, the microstructure that we were able to extract during our field activities. So for our in-house laboratory testing, we generally start with the non-destructive testing, which is initiated by visual inspection of the as received sample. So we look for failure or degradation features such as corrosion or initial cracking or bulging. So depending on the sample that is delivered to us, then we, of course, conduct more non-destructive tests such as dye-penetrant testing and radiographic testing and elemental analysis so that we can confirm if the specified material grade is still adheres with the original one. So after the non-destructive test, we do proceed sectioning, which is the destructive part of this in-house laboratory testing, so that we can produce samples for dimensional analysis to quantitatively describe erosion or bulging, if there's any, and metallography with our, what do you call this? A tabletop grinder and polisher. So this is the resulting section from sectioning. So these are the parts that we analyze for metallography, and of course, hardness testing to describe its mechanical properties. So note that the tests applied may vary depending on the requirement of the analysis. So since we are broadening our testing capabilities, here are some of the methodologies that we are currently developing. So first is the deposit weight analysis. Basically, this test aims to quantify how clean the boiler tube sample is, because over time on a boiler tube's operation, scales or deposit accumulate on the inner surface of the boiler tube. So we use chemical reagents to strip off the deposit scales, and we calculate the loss of mass recorded from the initial from its initial condition to the immersed condition, so that we can quantify if the part needs cleaning or not. And deposits actually in boiler tubes can cause inconsistencies and deviations in heat transfer within the tube walls, which may cause localized heating and eventual failure. So this is a really important testing for boiler tube applications. And of course, fructography. So we are increasing our knowledge pool on the different fracture surfaces so that we can accurately describe the failure mechanism or how the crack propagated for a certain sample. Yeah, so now that the capabilities were discussed, I'll now proceed to the general discussion of what we have done, the analysis that we have done on the field and in the lab so far. So, of course, we take the processing history, operating parameters from the client, then we proceed to non-destructive testing, microstructure analysis, and other material characterization tests to supplement findings from the microstructure analysis. So first, one of the features that we are mainly looking at in high energy material components is creep damage. So creep damage is a temperature and time dependent failure. So eventually, a boiler tube in service for a very long time will will pose deformation, and this deformation is manifested on the microstructure by this crack. So this figure is an example of a micrograph that we have taken from one of our lab testing. So as you can see here, there are voids, creep voids, as we can call it, and they are starting to orient to form a crack. So we have our reference here, and these are the stages of creep. So we have primary, we have secondary, and tertiary creep. And from the qualitative assessment of this micrograph, we have concluded that this specific component is currently around this part in its creep stage. So it is on the secondary stage, and the conclusions or the recommendations that we can give for this is to further observe and monitor the development of these creep voids if it orients to form microcracks. But intervals should be adjusted to make it more frequent. Yeah. So next is spheroidization. So spheroidization happens in carbon steels when exposed to temperatures in the range of 450 degrees Celsius to 760 degrees Celsius for a long period of time. So here, the carbides on the microstructure were given enough time and energy to diffuse, to coarsen, agglomerate, and stabilize into spheroidized carbide. So these spheroidized particles or carbides eventually disperse on the microstructure and result to a loss in mechanical properties, particularly hardness. So this spheroidization makes the component softer than it is expected. So also causes a reduce in creep resistance, which I have mentioned earlier, which again is detrimental in high energy components. So here are some of the micrographs or the replicas that we have acquired during the field, and it shows the microstructure evolution. So we have here, this is like the healthiest na microstructure that I can find on our data. So as we can see here, the carbide grains are still intact, and as we go through, this carbide starts to agglomerate, they start to coarsen, and they start to disperse out of the microstructure until it reaches to this point where all of the microstructure or the spheroidization and the carbide degradation is complete. So from here we can, although there are no creep damage that is observed here, we can conclude that this specific part has already spheroidized advancedly so that creep damage can be expected anytime sooner. Yeah, so these are just the carbides. And next is graphitization. So another degradation mechanism, which is the decomposition of carbides into iron and carbon, which is the graphite. So the presence of graphites in the microstructure can embrittle steel parts, especially when graphite particles form a continuous zone through a load carrying member. So it is thermodynamically favored over spheroidization at temperatures approximately below 550 degrees Celsius. So unlike spheroidization, this requires a lot lower temperature, but still, this temperature is within the range for the high temperature components that we are examining here in FA Hub. So I'll show you example of microstructures with graphitization. So as we can see here, these graphite nodules are found randomly within the microstructure at the base metal, at the heat-affected zone part, and this can act as stress concentrators in the microstructure, and that's why we are also concerned in observing these microstructures in our samples. So next we have sensitization, which occurs mostly in austenitic stainless steels. And this happens when chromium reacts with carbon in steel to form chromium carbide. So as you can see in this figure, so what makes stainless steel stainless is its chromium content. So the chromium actually forms a passivating layer when it reacts with the oxygen on the environment, and that passivating oxide layer protects the stainless steel component from from corrosion. But when sensitization occurs, so the chromium available for passivation gets depleted because it gets sensitized within the grain boundaries of the microstructure. So it will produce a chromium depleted zone, and thus it reduces the corrosion resistance of our sample. So this is also an important microstructure degradation feature to look in high temperature members. So okay. Shown here is a sample that were given to us for in-house laboratory testing. This is a stainless steel sample, and we have taken the microstructures from the two different parts, so one at the top part and one at the bent part. So as you can see here, we can observe that the grain boundaries are coarser than usual. So yan. I have annotated the features. So this shows that this particular component experienced sensitization. So it has generally lower corrosion resistance that it is compared to its original form. And here at the bent part, we have, since this bent part is cold work, we have here dislocation planes within the grain boundaries. And since these points of dislocations are high energy, so the carbides can make precipitate towards it. So that's why there's sensitization happening within the grain boundaries as well. So this is what we are trying to look at when we do microstructure analysis. So we can conclude that, of course, this part is already on it's already degrading. Okay, so another thing is the welding defect. So this is more on the processing side of the component. So we have here a ring section of a welded boiler tube. So we acquired the microstructure from this part and this part, which are welded. And looking at the zoomed images of these parts, it seems like that there is no any void or defect observed, but we can observe the interface between the welded part. So we have the base metal and this one, so we can observe the heat affected zone and such. But when we when we get the microstructure at this point, so it was revealed that at this interface there is a void observed. So this void that it cannot be really seen with the naked eye, can only be seen when we observe the microstructure. So we can see that there's a lack of penetration, even though it is very small. There's a lack of penetration between the interface. So it just says a lot about the quality of welding applied in this part. So ayan, as we can see, although the crack tips here are oxide field, so that is how we confirm that this is from the welding process itself and it's not surface induced. Still, these points can act as a stress concentrator. So that's why we are also very concerned in observing these types of defects, especially for welded components that is uh, really statistically very prone to failure compared to the base metal. Ayan. So why does this microstructure analysis matters? So these evaluations give us a very clear idea on how the component could behave when it is in service from the microstructure and the properties tested, and its performance can be described as well. So the findings also allow us to recommend points for improvement in the operation and maintenance. This also ensures that the interventions to be done is science-based and is backed up by data, which makes it truly effective. Since the failure analysis and metallurgical evaluation is an effective tool in preventive maintenance, the corresponding recommendations will allow for a smoother operation, from the reduced and unexpected shutdowns due to component failure to adjustments in the operating parameters to ensure material quality sustainability. So basically, we aim to translate these findings to propose concrete industry solutions. That is why we focus on uh, forging solid partnerships in the industry so that we can use our capabilities, our skills, and specializations to aid in the operational improvement. So FA Hub can serve as the bridge between the technicalities in the academia and the practicality in the industry, proving that both can work hand in hand together to produce meaningful impact. And even though currently, sorry, and even though currently we are focused in power generating industry, we aim to expand our collaborations with other industries in need of this type of service, as this type of research work is definitely in need. So, yan. Nauna rin thank you. So that's all. And together, let's work to use the microstructures to create macro impact. And have a great day ahead.
Yeah, we appreciate the technical expertise and captivating insights shared by Sir Nathan. Thank you for letting them take a glimpse at the work that we do at FA Hub. So now, we shall transition to the awarding ceremony for our oral and poster presentation. Sorry. Okay, so before we reveal the winners for the oral and poster presentations, we would like to welcome our program leader, Engineer Stan Christian Ejera, for his project leader's address.
Hello, good afternoon everyone. Thank you for coming to this event. No? I'll keep this short kasi medyo thesis defense yung ginawa ni Nathan. No? Okay, so hopefully I'll finish within 10 minutes lang or 5 to 10 minutes. Okay, so my talk today is entitled AI Cross FA, the Future of Failure Analysis. So, Larry, ayaw. Hindi pa na focus. Ayan. Okay, so just a brief background. No? When we talk about AI, yung initial talaga na naisip natin is AI in terms of LLMs, no? Yung large language models like ChatGPT, Claude, Gemini, etc. Which is okay naman, no? Engineers or professionals use LLMs a lot, but in terms of engineering, yung mas useful talaga sa atin when it comes to AI is actually machine learning, no? So machine learning, we can sort of briefly define it as just the science of teaching computers to recognize patterns and make decisions from experience. If you really think about it, if you look at the simple definitions, no, it's we can highlight keywords here. We have recognize patterns and make decisions from experience. And if you think about it, that is what failure analysis is all about. No, we feed from our experience, from our testing results. We recognize patterns from those testing results, and we make decisions that will improve our process or whatever the failed part is. Okay, so. If you're into AI or you're studying AI, you will learn that machine learning under the hood is essentially just a very superpowered na applied statistics, no? If you look at the science behind it, parang statistics lang talaga siya. Pero, and some jokingly say na AI or machine learning is just statistics that has been marketed correctly, no? Parang ganun yung joke nila. Okay? So, oops, nawala ulit yung focus na, sorry. Doon sa, i-click mo lang. Thank you. So we talk about how AI or machine learning can be applied to failure analysis. Let's just talk about some of the key differences when we try to apply AI versus the traditional way of doing it. So when we do traditional FA, usually it's time-based, fixed yung schedules natin. Pero when it comes to ML-powered AI or ML-powered, pwedeng condition-based and real-time yung triggers natin. So instead of relying on preventive maintenance schedules, magre-rely tayo on sensors that can trigger, that is AI-driven and can trigger those conditions. No? Next, we have static thresholds or alerts. Usually, this is in the form of statistical process controls. No? Meron lang tayong upper limit, lower limit. Pag lumagpas, then we say na out of control yung isang process. Pero in AI or ML-powered, we can have multivariate pattern recognition. No? So we can have multiple variables, and we can look at them at the same time, and AI can detect whether there is a anomaly in those patterns. Okay? Next is isolated variable monitoring. Traditionally, pagka you're using traditional FA, usually it's 1 or 2 variables lang yung tinitingnan nyo. You can do 3 variables. For the more variables, if you look at traditional na para design of experiment, no, more variables means more experimentations, and most likely hindi kaya ng amount of time mo para ma-analyze yun. Pero if you have AI or ML, you can have those multiple variables studied at the same time because the algorithms will enable you to do so. Okay? And usually, pag AI, it's always or almost always reactive in nature, no? Parang break-fix mentality siya. If something breaks, you figure out why it broke and you fix it and then prevent it from happening again. Pero pagka AI powered, we can have a proactive failure prevention. That's not to say na traditional is not proactive, no? There are a lot of traditional na failure analysis that is also proactive in nature, pero AI or machine learning will enable us to do so. Now, that is not to say na AI is a magic parang tool, no? We can think of AI as a black box, pero for us to open that black box, kailangan pa rin ng engineers. So, hindi naman to ibig sabihin, no, pagka nag-AI powered na tayo na failure analysis, wala nang kwenta or wala nang silbi yung mga FA engineers, no? So we're not trying to do that kasi mawawala din ng trabaho yung mga metallurgical engineers, no? So hindi yun yung goal, no? Kasi again, AI and ML is just a tool. So it just enables us to do things that previously weren't possible because we have now algorithms that can help us uncover the black box, no? Okay? So, and this is what we call as in AI, no, as physics-informed na machine learning. So, when it comes to the black box, ang gusto natin is i-inform natin yung black box natin of the physical limits or physical na parang theories related to that system, and it makes for it such that yung black box natin, instead of just a magical black box, pwede siyang engineered black box na siya that we can peer in our eyes into it. Okay? So, some examples lang of examples of how machine learning or AI can be applied. One example could be anomaly detection, such as an early warning system. So this is to identify yung off-normal states. No? So you can have unsupervised learning algorithms like isolation forest or autoencoders para makapag-establish kayo ng high fidelity na normal profile behavior. And this is exactly how banks actually, no? Ganito yung ginagamit ng banks para ma-determine kung meron fraudulent activity doon sa ano nyo, sa account nyo. Kasi it gives you a profile kung ano yung normal na behavior nyo. Okay? Now, if you look at the right diagram, no, parang siyang, it looks like an SPC diagram, parang typical na statistical process control na. So that's what I was saying, no, na parang ang machine learning is a parang super version lang talaga ng traditional statistics. Now, if you look at SPC, usually one variable lang yun. Tapos meron kang upper limit, may lower limit ka. Tapos pagka lumagpas siya doon sa limit na yun, magte-trigger siya ng warning. Pero AI can handle multiple variables. No? This could be as high as 100 variables. No? So 100 variables at a time. So think about it. 100 parameters, sabay-sabay niya tinitingnan. Tapos tinitingnan niya yung 100 parameters na yon alam niya kung ano yung normal. If one of those variables stray off, you can have an early warning detection system. That variable has an effect on the product or the process line. Next, we have your clustering models. So there are many clustering models. You've probably heard some of yung mga PCA, DBScan, K-means, mga ganon. So essentially, clustering is just uncovering patterns. No? So usually when we have, high dimensional spaces or yung spaces na kumbaga masyadong maraming variables na tinitingnan, sobrang hirap i-determine kung ano yung parang relationship between them. So itong clustering models, they sort of cluster your magpo-form siya ng different groups, and from those different groups, you can derive certain patterns, no? So it can be a tool for discovery para makapag-identify tayo ng parang groupings for specific na mga operational signatures yung tawag natin. No? Operational signatures is essentially the parameters, no? So for example, a certain set of combination of parameters usually lead to this type of failure. Tapos pagka different set of operational parameters naman, it could lead to another type of failure. So that is what clustering models can help us do. No? Next is yung predictive life cycle. This is a regression model lang. When we have, kunwari, if we have a history na alam natin na ito yung rate of degradation, then we can estimate yung ano yung remaining life ng process natin or ng product natin through regression models. Etong regression models, again, this is just the same as in statistics. It's just a souped-up version na kaya niyang multiple o high parameter or high dimensional spaces. Next is computer vision and defect classification. So this is how AI is traditionally used in AI is emergingly used in the semicon industry. So pwedeng ang gawin natin is we can feed AI data like micrographs or optical images, and from those images, it now detects kung anong yung klase defect ang meron siya. So something like pwedeng flat defect, linear defect, pattern defect, complex, etc. etc. Parang gano'n, no? So this is similar to how how AI detects if it's a cat or if it's a dog, if it's an apple or if it's an orange, parang gano'n, no? So you've seen those types of technology, pero it's rarely used in engineering, no? So why not use it in engineering? Kasi if you think about it, failure analysis, a lot of our analysis actually rely on images. So if we can harness this tool to make our lives easier, parang we can set up automated processes to help us determine itong mga defects na to automatically. Okay? And lastly, Bayesian optimization. No? Bayesian optimization is just a faster way of finding an optimized na configuration without extensive experimentation. So if you look at the image to the right, this is sort of a response surface, no? So this is how your material behaves. So this is a simplified version wherein parang may 2D space ka lang, kunwari 2 variables ka lang, tapos makikita mo yung valleys and hills na yan is the response surface. So kung mataas siya, whether you want it high or you want it low, depending on the parameter, no? Kung defect siya, you want it low, pero kung something like yield, you want it high. Parang gano'n, no? So what this is saying is, if you want to explore this space, traditionally, dapat you have to do extensive na experimentation, no? Kasi when you do experimentation of this nature, parang usually grid type siya, no? I-explore mo yung far corner, then yung next far corner, then sa middle, etc., etc. So it's an extensive work. So imagine kung two parameters lang, sobrang dami na ng experiments na kailangan. Pero if you go into higher levels of or higher number of variables, then you'll have your experimental runs will explode, no, exponentially. So that's why Bayesian optimization is a great tool or a great algorithm for us to streamline those processes. No? Instead of relying on the grid pattern, ang ginagawa ng Bayesian optimization, it's an algorithm that is smart enough to navigate the response surface. No? So parang kung saan niya tingin malapit na yung peak or malapit na yung valley, doon ka ililid niya sa optimized parameter na yun. So we've done theoretical experiments now on this doon sa mga classes na attend namin. So something like traditionally it takes 48 experimental runs, pero using Bayes op, parang in 11 runs lang, nahanap na yung same optimum. So something like that, no? Sobrang bilis niyang makakat off. So yun lang yung mga, just a peek, a preview of what AI can do for machine learning, or machine learning can do for failure analysis. Pero if you notice, yung mga sinabi ko dito, no, hindi lang siya limited to failure analysis actually, no? Parang pwede itong i-expand in any engineering discipline. That's why it's important na parang i-embrace natin yung AI, no? And if you're a third-year student, enroll kayo sa mid-year. Meron tayong elective on machine learning, no, offered. Ako yung mag-offer with Sir Ed. So kung gusto nyo, pwede kayong mag-offer, no? And with that, I end my presentation. Thank you so much for coming in today, and I will... Ay, di pa, may ano pa tayo, may a few appreciation. Tapos, after that, we'll give you to Sir Tito for the rallying remarks, no?
Thank you, Sir Stan. So, now, may we please invite to the stage Doc Les for awarding of the Certificate of Appreciation to FA Hub Class Industry Partners.
So good afternoon ulit. For interest of time, kami na lang po ni Doc Mitch, I told the students previously na baka pwede silang umakyat para mag-hands na ng Certificate of Appreciation sa ating mga field FA partners, failure analysis partners. Kaso nga, medyo kailangan na po nating magmadali because we have extended a bit. No? So we'll start with, let me read first the Certificate of Appreciation citation here. No? So this certificate is proudly presented to the company in recognition of your valuable partnership and support as academic field activity partner of the MAT-E 173 or MET-E 179 classes held at the Department of Mining, Metallurgical and Materials Engineering, University of the Philippines, Diliman, Quezon City, given this 5th day of June 2026. So signed by the course handlers of these courses and Doc Mitch as our chair. So let me start with the Department of Science and Technology, Philippine Textile Research Institute, or DOST-PTRI, together with the direct partner supervisor, no, Philip Aljon M. Basat. Thank you. SEM Calaca Power Corporation or SCPC. Nandito pa ba? Wala na. Ferrotech Steel Corporation. Umalis na rin po yata. The UP Engineering Library, the Learning Commons, no, yung aming kapitbahay dito, yung TLC. Capital Steel Corporation, and Orthopedic International Incorporated. So far, those are our AFA partners. And we also have consultants coming from different specializations in the university, no, from different colleges and departments. Sayang lang wala sila ngayon, so hindi na namin tatawagin to save time. Thank you, and please continue to support us.
Thank you, Doc Les. Now to recognize the students' participation for oral presentation, may we please invite to the stage Sir Stan to award Certificate of Participation to the students. So, may we also please invite all the students who presented yung oral presentations kanina and their team members, please.
Sige. I'll just read the certificate. So this certificate is presented to a name of student for their presentation entitled the name of the presentation in Interface 2026, held on June 5, 2026 at the Department of Mining, Metallurgical and Materials Engineering, University of the Philippines, Diliman. So I'll read each name one by one. So first is Mariel Rose Loreto, then Dance Christian Aleta, Then we have Rene Isabel Garin. Then we have Jules Resano. Now we have presentations for the poster presentations. So this is awarded to the title of the study for their presentation in Interface 2026 on June 5 at UPD Triple ME. So the first award is given to number 1, understanding the failure mechanisms of pineapple leaf fabric tactical plates after ballistic testing. Then we have evaluation of ballistic performance and failure mechanisms on a Dyneema pineapple fabric reinforced hybrid composite armor plate. Then next we have failure analysis of fractured flying shear blades used in hot steel rebar rolling mills. Okay. Then we have investigation of the premature failure of the flooring system in UP TLC. Then we have investigation of the suspended ceiling system failure in an audio-visual room. Anong AV ko? Dito ba? Ay, sila ata. Si Verona to pang isa. Next, we have failure analysis of Philippine cotton weaving yarns. Then we have failure analysis of sleeve seam in Inaul handloom woven fabric garments. Then we have failure investigation of the heat recovery area, wall tube on a coal-fired thermal power plant. Mga METI yata to. Then we have another failure analysis of the furnace front wall tubes in a coal-fired power plant. Wala ata sila. I see. Next, we have investigating spud and circumferential weld defects, a case study on leakage in LPG cylinder tanks. Wala na ata sila. And last but not the least, debonded tile system in a building in UP Diliman. Okay? So, picture taking tayo. Baka pwede ba mag-blocking yung mga students?
O yung nakikita lahat.
Oh. Upo na lang yung or squat. Ayan na lang. Si, yung kila Chauncey. Sama kayo sa picture.
Sama kayo doon.
Uno.
Alright, sir, sa stage. Alright, for the presentation of the conferment of the Best in Oral Presentation Award, Doc Mitch and Sir Stan will confer the award for the Best in Oral Presentation, joined by Sir Mark. Sir Mark Cabet. Alright. Sir
Sir Mark Kabadi. Kabadi. Pwede din po si Sir Mark Buado. Sir Mark.
Perfect. So the best in our presentation award is the best in oral presentation award is the failure analysis of steam boiler pipes in a coal-fired thermal power plant. Representatives po ng group. Perfect.
Yan, Ako luto pala to.
Gitna na lang po ng stage. Thank you. Poster po yung next.
Alright. For the conferment of the Best in Poster Presentation Award, may we please invite Doc Les to join us on stage.
Ay, hindi ka pa na. Sir Edwin, kayo na lang daw po mag-confer.
Poster po. Best in Poster Presentation, yes.
Alpo. Sabay ka na. Kaso hindi ko alam yung title nilang dalawa. Ay, sige. Ay, dito na lang pala, ma'am. Dito na lang.
Alright, so for the best poster presentation, we have a tie. So it's a tie, guys.
Yeah, kaya pala dalawa.
So dalawa. So the first one is awarded to the study entitled Understanding the Failure Mechanism of Pineapple Leaf Fabric, UHMWPE, Silicon Carbide Tactical Plates after Ballistic Testing. And then the next award is awarded to the study entitled Failure Analysis of Sleeve Seam in Inaul Handloom Woven Fabric Garments. Congratulations. Alright, perfect.
Baliktad. Baliktad yung log. Hindi, tama yung sa'yo. Baliktad yung kanya. Baliktad, baliktad. Yan, okay.
Please remain on stage po, Doc Mitch. Next, we have the winner for the smoking gun exhibit.
The judge's choice, please.
For the judge's choice, for the People's Award muna. So, yung winner for the People's Choice Award of the Smoking Gun exhibit is none other than Therese Mangusad with the entry We Don't See Height to Height. With a whopping 57 votes. 27 pala, 27 votes. Sorry. Yan.
Perfect. Double time po, double time. Double time.
Alright, and the winner for the Smoking Gun exhibit, Judge's Choice, is none other than Nathaniel Bonita with his entry, Careful She's Watching. Perfect. us for the presentation of token to our Executive Director of the UP ERDFI, Sir Tito Aliga.
Go, Sir Tito. Yes. I put in.
So basahin ko na rin habang pa kay Sir Tito. So this certificate of appreciation is given to Alfonso Tito A. Liga Jr. for his invaluable contribution for, well, he to be delivering his rallying remarks in the Interface 2026, a joint academe industry failure analysis symposium held today at the Triple M Department, UP Diliman.
Picture muna, sir, dito. Picture muna? Oo. Sige, sama ko. Okay. Hawakan mo muna to. Sige.
Okay, so I was tasked or given the honor to do the closing remarks. I think we are running out of time. We are 4 minutes beyond 5 o'clock. And again, in Singapore, we don't allow that. Di ba, Mark? Okay. So anyway, I wrote down 5 points here that I would like to stress as part of this activity. Number 1 is the importance of collaboration. We can see here the partnership between industry, academia, and government in making things in what I call exponentiating our efforts. It's not 1 by 1 or 1 plus 1, but it is 10 times 10 times 10. So we exponentiate. That's the word I use. By collaboration, we don't add, we exponentiate. Number 2 is that it's important that our research is impactful. That's why when VP Joel Marciano was given the position of VP for Research and Innovation, I told him, sabi ko, Joel, it must be research implementation. Innovation, that's a nice word, but if it's not implemented, it's nothing. And fortunately, he agreed. Number 3, the importance of people. I think the presentation of Mark, Ansel, and Mayeth stressed. The bottom is always talent. It's people. And again, studying Triple M with your smart professors, with their experience like Leslie, then you are very lucky that you have these mentors. Make sure you learn. Okay. Number 4 is the importance of financial sustainability. Our laboratories, if we are really world-class, we must also charge world-class rates, not barrio-class rates. Okay? Just because UP, we cannot charge this, we charge 200 pesos per hour, it must be $200 per hour. Di ba, Mark? Otherwise, barrio-class tayo. If we cannot demand $200 per hour, we are not world class. And number 5, this is very important. We would like to thank Beach for 3 years of service in Triple M. Let's give her a big hand. And Kath, where are you? And we must congratulate Kath. Please come forward, Kath. For taking over the reins of this of the Triple M. And as I always say in turnover ceremonies, and I said this before when Leslie turned over the floor to, who followed you, Leslie? Jong. You are not going to feel the shoes of Mitch. They are worn out. So we will cobble for you. We will make for you a new pair of shoes. Because the path is long, the road will be uncertain at sometimes. So you need a new pair of shoes. Don't take over the shoes of Mitch. Okay. Di ba, Mark? Oh, marami tayong tatahakin na baryo na eh. Kaya we will cobble for you a new pair of shoes. And kanina, I was talking with the cat how we can move forward. And I think it's the same thing, collaboration with UST. Let's have laboratories that are parallel or that mimic their own laboratories so we can collaborate directly. If they have failure analysis hub, we collaborate with them. Because by doing that, we build on what is already available rather than investing or finding new budgets for them. So again, talent, world-class billing rates, Singapore rates as much as possible, at least. But again, it's not 200 pesos per hour, it's $200 per hour. So again, thank you very much, ladies and gentlemen. Thanks for giving me this opportunity.
Thank you, Sir Tito. We thank everyone for their presence and participation. It is our hope that the connections established today lead to a safer and more innovative engineering landscape. Safe travels to all and have a pleasant evening. So please answer na lang yung evaluation form namin to receive your certificate of attendance sa email. Thank you. So, may we please invite lahat po ng FA Hub staff sa front for a group photo. It's a wrap, guys. Congratulations for the job well done. Job well done.
Pati sila, sila Kuya Onyok, tsaka Kuya JR.